So let's go into the examples in terms of machine learning and forecasting in code. So we'll be using Python in Colab, and I'm just going to pull in some libraries that I need to use, and then also I'm going to pull in the data as well. So this is the Shark Tank data, and you can see what that looks like. All right, so I see my data set, and then I also see the variables in the different columns. So we're going to start with linear regressions. This extra package, Tabulate, is just going to help me sort of summarize the regression results in a prettier table. And then I'm going to limit the data to just a certain subset of fields and then use those. So original ask amount, total deal amount, valuation requested, and number of sharks in deal. That's my subset of data. And then to start out, I'm just going to use a simple linear regression. So I have the single independent variable, original ask amount, and then also the total deal amount. Here is my dependent variable. So we're going to run this, and I'm also going to produce our accuracy metrics as well. So we'll take a look at those outputs. So simple linear regression, it actually tells us that in looking at that coefficient or that slope, for every 1 unit increase in the original ask amount, I expect the total deal amount to change, in this case increase by 1.009, or basically $1, around $1. So for every 1 unit increase or $1 increase in original ask amount, I expect the total deal amount to increase by 1. And that is statistically significant, so I can make that statement, write the p-values very small, basically close to 0. And you can see my prediction metrics as well. These first three don't mean as much unless I'm comparing this to another approach or another technique, which we'll do in a bit. So you can see the R squared, 77%, so 77% of the variance is explained by the model. In other words, 77% of the variance in the total deal amount can be explained by the original ask amount. And you see that prediction line here as well, and obviously we're off, in some cases off by quite a bit for some of these deal amounts, and you can see that discrepancy, that difference, and then you can see that obviously this is going to correspond to our slope, or how this line moves up in terms of the predicted values as a function of the original ask amount. But what might be helpful for us is just to understand the units again. So this is the total deal amount, or the dependent variable. You can see the in units. I'm just going to print this because it's in scientific notation. Right, the average deal amount is about 293,000, and you can see that there. So it just sort of gives us some context with respect to the units in terms of what an average value corresponds to for that dependent variable. This would be the full output, or what you would naturally see without the formatting that I added on. But you can see that, again, I'm getting the same information, right? The relationship between original ask amount and deal amount that's shown here. The R squared is shown at the top, and then also the p-value associated with the original ask amount coefficient. What this is here is this is actually in a confidence interval. I mentioned you could use those as well for hypothesis testing. And basically, if we had a situation where this coefficient, the interval actually contained 0, we would actually get a p-value that's larger than 0.05, right? So we wouldn't be able to reject the null. In this case, the p-value is actually less than 0.05, so we can reject that null hypothesis. And that confidence interval doesn't contain 0. So when we think about this, is most phenomena are not able to be studied just using a single independent variable. So we might use several independent variables. In this case, you can see we're going to use the original ask amount, valuation requested, and original offered equity, right? So we're just going to use those variables as predictors for the total deal amount. So we'll go ahead and run that, and you'll actually see that we'll get coefficients here, but there's multiple. And the original ask amount, again, it's pretty similar for every 1 unit increase in original ask amount. We expect the total deal amount to change by 0.97, controlling for all other factors, or controlling for the valuation requested and controlling for that original offered equity, right? So we have to add that extra statement, controlling for other variables, when we use multiple regression. And in fact, valuation requested is significant, but the effect is fairly small, right? When you increase in valuation requested, controlling for other factors, there's a 0.0033 increase in the total deal amount, and it's on the border in terms of significance, right? 0.047, still less than 0.05. But in fact, the original offered equity coefficient, it's negative, but it's not statistically significant, right? So we can't really make any statements around this because we cannot reject that null hypothesis, that there is no relationship between X and Y. In this case, X is the original offered equity amount. All right, so we have our error metrics. In fact, if I just look at mean absolute error, 57,475, right? So on average, we're off by 57,475 using multiple. And then we look at our simple, 57,767, right? So there is actually some slight improvement by using the multiple regression in terms of the prediction accuracy, right? How off we are on average in absolute value. And the R squared's pretty similar, right? But I mentioned that these are really valuable when we're looking at comparing two approaches or comparing several different approaches or several different techniques. So if we look at our output, you can see the basic output, and that's sort of consistent with what we've already seen, just in a slightly different format. And one thing they did want to point out is there's actually a p-value here associated with the F statistic, and basically there what we're looking at is for that p-value, we're actually looking at the null being there's no relationship between any of the variables and Y. Alternatively, at least one does have a relationship, right? So the null is basically all the variables we have in our model are meaningless. Alternatively, at least one does have a relationship, or one is meaningless. Sorry, not meaningless. At least one alternatively is meaningful. And you can see there that we can actually reject the null, right? So we have some variables in our model that are meaningful, or they do have a relationship with Y, right? So some of these independent variables have a relationship with Y. So this is sort of an over model hypothesis test. And you can actually see here that when we look at the individual coefficients, we obviously do see two variables that are statistically significant, where they do have a relationship with Y. In this case, it's our total deal amount. One last thing we want to look at is, do we have, and linear regression does have a number of assumptions. One of the main ones that we're often concerned about is multiclinarity. So multiclinarity occurs when we have variables in the model that are highly correlated with each other. And what that does is it creates a number of issues, including statistical significance. We might have variables that should be significant and are not because of multiclinarity, or the magnitude or the size of the coefficient is not what it should be, or the coefficient is positive or negative when it should be the other, right? So it might be a positive coefficient where it should be negative, and then vice versa. So it causes a number, let's just say diseases in our model, and it results in really unreliable output or results. So we can actually check for multiclinearity. One way to do this is looking at the VIF score. There's different thresholds that are used for VIF. Let's actually, there's different thresholds that are used for VIF. Generally greater than 5, we should have some concerns. Over 10, definitely multiclinearity is happening here. So we don't really have any issues, right? We're all, you can ignore the constant. We're all kind of below 5, right? Definitely below 5, so we can sort of ignore that. And then we do see that when we look at our correlation coefficients, that we original ask amount and valuation, there's a slightly positive relationship there, right? Slightly positive relationship there, but not as much of a concern as I did look at the. So I did look at the VIF, right, and no red flags came up. But yeah, and then obviously we want these variables to be correlated with total deal amount, so you can actually see the total deal amount and original ask amount is actually highly correlated, right? 0.88. Again, this ranges from -1 to 1. Closer is to 1 on the positive side. You can see that it actually is very close, right? Almost 0.9 if I'm doing some generous rounding, and you can see that there. So we want that independent variable to be correlated with this guy. We just don't want the independent variables to be correlated with each other. So we're good there. So we've sort of checked for multiclinearity, and you can also see the scatter plots. Obviously, those go along with your correlation coefficients. Also, the distributions are shown kind of in this diagonal as well. So that would be an example of multiple regression. And I mentioned a lot of phenomenon need multiple, right? We can't just use simple or one independent variable. There's much more we can check, right? We can look at the error a lot more, or what's called residual analysis when we think about regression. But we just want to get a practical sense of how we might use linear regression, and then obviously in your own applications you would go in more depth and evaluate sort of every possible thing that could come up or could cause your results to be slightly unreliable in a regression setting. So if you look at logistic regression, again, we have a categorical dependent variable. Guess what? I'm going to use got deal, right? So got deal is the categorical variable I'm going to use, and I'm going to use these features or variables, including original ask amount, industry, gender, and then whether or not there's multiple entrepreneurs. So if I go ahead and run that, you can see I have a new data frame, or sorry, a new data set that just has those specific features or variables I care about. So I did some filtering and also created some 1 zeros. So we converted got deal to 1 0, and then also did some formatting with the variables as well. But now our industry variable, you can see, is actually there's a column for each industry, 1 0 column for each industry, and we'll be able to use that in our logistic regression model. So let's go ahead and run that, and there's a lot of output here, and I'll explain what all this means. So you can actually see here, I look at the original ask amount in predicting got deal. It actually doesn't have much meaning here, right? The p-value is not less than 0.05. You can see that odds ratio as well, but there's not really much meaning for the original ask amount, and there is all sorts of other output here that we'll look at in terms of the results, but some major takeaways for this is multiple entrepreneurs, right? So multiple entrepreneurs does have a relationship, right? And this coefficient's a little bit strange, and what's often helpful is to translate this to an odds ratio, right? Odds ratio. And the way we'd actually think about this is the odds of getting a deal are actually about 93% higher compared to single entrepreneur startups, right? So multiple entrepreneurs flag or sort of indicator suggests to us that there's 93% higher odds of getting a deal when compared to single entrepreneur startups. And the other side of this is you have an odds ratio above here at sort of 1. And that's for the original ask amount. Basically no relationship. So the near 1 odds ratio means that raising or lowering the ask amount doesn't really impact the success of getting a deal all that much, right? So it's not statistically significant. So I'm always looking at this relative to 1 with respect to the odds ratio. And when we look at the some of the industry effects, some of the odds are actually lower than 1. So for example, business services and the software and tech as well. It's got to be somewhere. So the business services, technology and software, right? So those are actually less than 1, or the coefficient is negative. And what that means is that those industries actually have lower odds of getting a deal. And you can keep going and look at these individual industries, but let's kind of look at the gender as well. So the gender, how would we interpret this? So in fact, for gender, male-only teams, you see this result here, male-only teams, they have a slightly lower odds of getting a deal. But wait, we need to look at the p-value again. And in fact, that's not statistically significant, right? So we basically what I'm trying to emphasize is we shouldn't be making statements about there being lower odds or higher odds when in fact the outcome is not statistically significant, right? So we always want to think about statistical significance in the context of reporting and also suggesting that there is a relationship when there isn't, and then vice versa, right? So that's something we want to keep in mind. We have a pseudo R squared. The pseudo R squared, it's very similar in terms of interpretation to the R squared and regression. In this case, the model explains only about 3%, sorry, 0.03, right? Only about 3% of the variance in got deal. So we're not really very happy with this, right? So possible fix would be we add some additional variables, but we're not really happy with that sort of 3% R squared or pseudo R squared. We definitely want that to be closer to 1 or 100%. And then we can look at our classification metrics, and you look at that classification report. In terms of precision, that's for the no deal. So about 59% were predicted predicted no deals were correct. So that's how we'd interpret that precision. Alternatively, for class 1 or the got deal, about 64% of the predicted deals were actually successful in terms of the prediction. So we can also look at the recall. I'm going to focus on the got deal now. So the model captures 90% of the actual deals, meaning it misses a true deal. And then for the F1 score, that's sort of a weighted balance measure of the precision and recall. And that basically says the model performs better at predicting got deal when compared to the unsuccessful ones, right? So 0.76 versus 0.29. If all else fails and you're confused, all right, precision recall, what is that? I'm confused. Go to the confusion matrix. So confusion matrix basically helps us understand of the actuals, how many were we right? So you see the actual no deal, predicted no deal, actual deal, predicted deal. So you can kind of see that that sort of match of the accuracy, or sort of evaluation of the accuracy based on predicted class. And you're probably wondering, okay, well, I thought you said we're going to use a probability. In fact, we're saying that if the probability is over 0.5, we're predicting class 1, otherwise we're predicting class 0, right? So that's what we're going to use. We're using that default value in that example. Yeah, so if you look at the sort of, yeah, and what we could actually do is we could actually sort of evaluate the overall accuracy. In this case, I need to adjust my numbers. So 546 is the times I was right on the actual deals, and then 71 was the times I was right on the actual no deals. I'm just going to copy that over, right? 546 plus 71, and then the balance is obviously 49 and 305. That's where we missed here, right? So you can see I'm basically taking the hits, actual no deal, predicted no deal, and then actual deal, predicted deal. Those are the hits, and we fill those in, and that gives me an overall accuracy about 63%. So I don't feel all that excited, right? With an overall accuracy of 63%. So there might be some other features or other variables that might be helpful in interpreting why certain entrepreneurs or why certain startups get a deal and why certain startups don't on Shark Tank, right? I want to improve upon that accuracy or improve upon that prediction accuracy. So that's classification. There's other sort of metrics you can look at, but that's just a sample of some of the metrics that are commonly used. And finally, we're going to go into time series. Yeah, the Shark Tank data set's not really it's not really the ideal data set for time series problem, right? You might be looking more so at sort of stock prices or sort of monthly sales. But one thing we can see here is actually the viewership, right? So we have the air dates and we also have the viewership. So we might actually predict or forecast the viewership. So that's going to be our dependent variable. And then we're going to use the date or the original date, air date, as the time period. And we're first going to fit a exponential smoothing model. So we're going to fit that exponential smoothing model and also similarly develop our accuracy metrics. But in this case, we're actually going to use a training and test split. So why do we actually do that? We actually do that because we want to sort of understand how well a model is going to perform to some unknown future point or unknown data, right, in the future. So we're actually going to use 80% of the data or 80% of the air dates to train the model, and then we're going to evaluate the accuracy on the 20% we're not using to train the model. And that's often common in predictive analytics projects, to train the model on a larger subset and then evaluate the accuracy on a subset you didn't use to train the model on. And the reason for that is we want our model to generalize, right? We want our model to generalize well. So we're trying to evaluate, okay, well, if I release this model out into the wild, how well would it perform on some new or unknown events or unknown data. So we're going to use that in this case, and we could have used that for the regression model and evaluate the training error or training mean squared error and test mean squared error. And we're going to use that, and we could have used that for logistic as well, right? Training and test. We're going to use it in this case for the time series. So we're going to take the sort of initial front period, or the 80%, front 80%, and then train the model on that 80% and then forecast going forward. So we can kind of see the differences between actual and forecasted. So we're going to use that exponential smoothing. And you can see there, this is the data we use to train, right, in blue. And then this is the predicted values, and then this is what actually happened, right? So we don't really feel too good about this exponential smoothing model, because in fact, we would be pretty off if we went forward and actually suggested that this viewership would be that that value there you can see in red, and what you can see here is the accuracy metrics are going to be similar, right? Mean absolute error, mean squared error, and then root mean squared error. We can sort of compare that if we have a model to compare that to, but that's going to be based on that test period. And if you could see here, you can see the predictions, right? So the actual prediction values for those periods going forward is actually 3.9. And you can see where that is, right? The US viewership 3.9, and where that actual value fall, or where that actual value ended up across those error dates. So it's actually interesting, though. You can kind of see that there was kind of higher viewership, and then the viewership kind of declined, and then sort of stabilized again, and then declined again. So it's very interesting to see the time series plot. But maybe we also then try ARIMA. So you need to install an additional package here. So we're going to try ARIMA. And what we'll similarly do is split the data into training and tests, and then evaluate the accuracy. There are components to the ARIMA, and we're not going to get in depth in that in the demo, but there is some additional explanation around ARIMA in the chapter. But what we'll actually do is we'll do something similar where we try to predict that US viewership as a function of the error date, right, or the time period. And you can see that there, right? We can see our data again, and then the predicted values, and our predictions are slightly different, right? They are slightly different. So you can see how ARIMA's predictions or forecasts are slightly different. And again, the mean absolute error, if I'm focusing on that guy, it's at 0.58 for the ARIMA, and it's at 0.6 for the exponential smoothing. So in this case, if I wanted, if I had to choose between these two, I would choose the ARIMA because it actually results in a lower average error, right? Lower average absolute error. Okay. So obviously you saw there that last point is that linear regression would not work for this, right? It's just way too volatile. So we would need to use a more sort of time series specific approach if we only had the time period. And then our dependent variable in this case would be the viewership. So finally, we can see if I want to do some auto ML, I'm going to bring in some additional packages here. Whoops. Gotta wait for install. Yeah, so if I listed out, a bunch of features, and I'm still looking at the got deal, I can use what's called lazy predict, right? There's a number of AutoML packages. I can use lazy predict. In fact, I'm using lazy classifier or sort of a sub library. But you can also use lazy regressor, right? If you have a regression problem. So I could also apply this to the regression problem and use lazy regressor. And basically what I'm doing is I'm feeding in a bunch of variables. And I'm letting the machine or computer tell me what's going to give me the most accurate outcome. So if I run through this, I can see, I'll just show you, it'll take a little bit of time to run. But in this case, again, we're going to use that training test regimen again, and it's going to evaluate the accuracy on that test data, because again, we're trying to generalize to some outside or new data. So there's all these different models or techniques. So these are more advanced techniques at the top. It's basically telling me that I can get to a accuracy of 60% as sort of as the max, right? Using this approach. And where's our logistic? So there is a version of logistic that gets us at about 57% in terms of logistic. But that's basically giving me a menu of different techniques or machine learning techniques that I could use to get to a certain accuracy, and it's going to sort by the accuracy, right? Sorting by this balanced accuracy from 60% all the way down to about 49% when we look at the decision tree. So when we think about this, is we might look at using sort of other variables. Maybe we can get this a little bit further up, or maybe we could sort of try another automated ML technique or approach. But this is, again, we're not really getting much information or much interpretability from using this process, but at least we kind of know the baseline in terms of what we could achieve based on the data that we have. And I just fed in sort of sample predictors or sample features, but you can see that very quickly I could get a predictive model that I could then use. So that's going to wrap up the Colab or Python demo, and that'll be the sort of end for Module 9 in terms of application.